In this video, we're going to finish off section 3.1 on the functions of several variables by doing example 3.1.4 and example 3.1.5. So example 3.1.4 asks us to make a contour plot for the hyperbolic paraboloid z is equal to x squared minus y squared, whose graph is given here on the right. So we are supposed to examine values, level curves. So we're supposed to examine z is equal to x squared minus y squared. Let's call that a function f of xy, and we want to examine this for different values of k. Equally spaced. For a contour plot, it's important to take your k values equally spaced. So we'll start with k equals 0, then we'll move up and then maybe down below 0 as well. So when k equals equal to 0, we've got x squared minus y squared is equal to 0, which is saying that y squared is equal to x squared. And so there's two possibilities for that. Either y is equal to x or y is equal to minus x. So these are level curves. These are points on the surface where all points on the surface that have the same z value, the same height, in this case a height of 0. So if we plot these curves in the xy plane, here's our line y is equal to x, and then our line y is equal to minus x. And now what we do on a contour plot as well is we write in the k value. Or we color code in some sort of way, but if we're making this a graph in just one color with just a pen or a pencil, then you write in the k value. So now we want to take a different k value, k equals 1, so I'm going to take a unit spacing, which means that I have x squared minus y squared is equal to 1, which we hopefully recognize as a hyperbola. If you forget whether it faces left, right, or up, down, I always remember by looking at the intercepts. So if I imagine that x is equal to 0, the y-intercept, well, if x equals 0, I've got y squared is equal to minus 1. That can't happen. So if I look at the other intercepts when y is equal to 0, I've got x squared is equal to 1, or x is plus or minus 1. That can happen. And that is how I remind myself how these graphs go. And then their hyperbolas, we know that they approach those two lines asymptotically. So I'll just go and draw in some approximately hyperbola shaped graphs, and again label. So this was when k is equal to 1. Going up, k is equal to 2, evenly spaced. So I'm going to get x squared minus y squared is equal to 2. Still a hyperbola. This time its intercept, so this one was at 1. Its intercept is going to be at root 2, which is about 1.4. And I'll add that curve in. And I'll get the same thing on the other side. And I can imagine, so this is when k is equal to 2. I can imagine k equals 3. I'll get root 3, which is 1.7. So those curves are getting closer together, which is something that we will talk about in just a moment. Okay, so what happens when we go down from 0? So let's say we have k is equal to minus 1. K is equal to minus 1, then I'm getting the curve x squared minus y squared is equal to minus 1, or rearranging it, y squared minus x squared is equal to 1. So if I do the same kind of calculation, it shouldn't take me much to figure out that these are going to be facing up, down, or opening in the y direction. So I'll go and add in hyperbolas in that direction. And the same thing when k is equal to 2. I better label this. K is minus 1. When k is equal to 2, I'm going to get root 2. And same thing, when k is equal to 3, I'll get root 3. So there's a very rudimentary plot, contour plot, for our hyperbolic paraboloid. Now, strictly speaking, that's all the question asks me to do, although I should label it. I forgot one, didn't I? This is k is equal to 2, and k is equal to -2 and -3, I plotted. So that's all the question asks us to do, but we can actually see a little bit more. We can see a little bit more. For example, this flat spot right here, that flat spot, we can see that right here on the graph. And from the flat spot, we can see that the values of k are increasing in the x direction. And if we go in the x direction, right, these are our values of k which are increasing. We can see sort of adding up this way that we're going up. So we can imagine the surface building up in the x direction because those k values are increasing. Now in the y direction, the curve is going down. And you can see that on both sides. In the y direction, those values of k are going down from 0. So you can see when the graph is increasing, you can see when the graph is decreasing, but more than that as well. We said that the graph, those contour plots, were getting closer and closer together, right? They're quite far apart around the origin where the graph is flat, and then they're getting closer and closer together. When they're getting closer and closer together, what happens to the graph? It is getting steeper. It's steeper because they are equally spaced for the same z value. Closer together in the xy means that the graph is getting steeper. So that's the remark that we have here. Because the k values are taken as equally spaced, the steepness of the graph, of the surface of the graph, can be judged from the contour plot. When the contour lines are closer together, then the graph is getting steeper. And consequently, when the contour lines are further apart, then the graph is getting less steep. Let's do example 3.1.5, which is the same kind of idea, except we're going to be describing in words the level surfaces of a function of 3 variables. So I want to examine again constant values. So I want to examine places where w is equal to k. So in other words, x squared plus y squared plus z squared minus 1 is equal to k. And from our study of quadric surfaces, we recognize this. If I bring the 1 over to the other side, that is the equation of a sphere of radius, the root of k plus 1. So in words, what do we have at k is equal to minus 1? We have a point. When k is equal to minus 1, we get 0 here, and the only way that you can add 3 squares to get 0 is if they are all 0. We have the point of the origin. And for increasing values of k, as k increases, we have concentric spheres centered at the origin. So concentric spheres centered at the origin with increasing radius as k increases, with radius the root of k plus 1. That's what the level surfaces look like of this function that's given to us here.